Hello, everyone. My name is Shahrzad, and I'm currently a research fellow at Northumbria University. And I'm very glad to be able to show you our results. My presentation is about an integrated, flexible platform of electromagnetic metamaterials and acoustofluidics on Kapton. The outline of my talk is that I will explain our aim, and I will give a brief introduction on the operation of metamaterial-based resonators as well as surface acoustic wave actuators. I will give examples using our previous designs and how we have come up with the design on Kapton, and I will end my talk with conclusions. So our aim is to combine sensing capabilities of metamaterial-based resonators and actuation capabilities of SAW devices on a single electrode design. We do this to achieve high precision sensing in microwave frequencies using metamaterials and to achieve fluid manipulations in radio frequencies using surface acoustic wave devices. And our ultimate goal is to move this platform on a flexible substrate for benefiting from wearable applications. Metamaterials are artificially engineered structures that have unique electromagnetic properties, such as having negative values of refractive index. There are advantages because they can be non-invasive and can be used as wireless sensors with high precision and sensitivities. Split ring resonators or SRRs are among basic building blocks for metamaterials, and they can have applications in a broad range from microwave to visible light, and high quality factors larger than thousands are achievable using SRRs, and they're also suitable for wireless sensing applications. This photo shows a review study where metamaterials were used as chemical and physical sensors throughout the past 10 years. So split ring resonators are basically metallic structures that have one or more splits on them and are fabricated on a dielectric substrate. So when these structures are exposed to electromagnetic waves, they can show some resonances, and these resonances can either be electric or magnetic or a combination of both. When a circulating current path is induced inside the ring, the resonant frequency would be called magnetic resonance. And the fundamental magnetic resonance can be modeled as an LC model having an effective inductance and an effective capacitance. So we can achieve magnetic resonance through different scenarios. One is when magnetic field is perpendicular to the surface of the device, therefore a circulating current path is induced inside the ring. The second case would be the magnetic field being perpendicular to the surface of the device, but also the electric field is polarizing the gap and is contributing to the circulating current. And the third case would be when it's only the electric field what is generating the circulating current path inside the ring. SRRs have various applications. So I have two examples in this slide. On the left-hand side, you can see the structure that I showed you previously, where it was used to sense different concentrations of heparin. And by increasing the concentration, the effective capacitance was increased, and therefore the magnetic resonance was shifted towards lower values. On the right-hand side, a rectangular embroidered resonator on a fabric was wrapped around an empty bottle and was placed in between two monopole antennas. And we could observe that when we fill the bottle with different substances, such as methanol, ethanol, acetone, IPA, and DI water, the magnetic resonance changes. So this is a way of sensing what is inside the bottle and can be used as a chemical sensor. On the other hand, surface acoustic wave actuators have been investigated for their microfluidic capabilities. So surface acoustic wave devices are basically metallic interdigital transducers that are fabricated on a piezoelectric substrate. And when power is applied to the electrodes, surface acoustic waves are generated, and these waves will travel along the surface. And when they encounter a droplet, the wave energy will be leaked inside the droplet, and therefore different phenomena can happen. These can be either mixing, pumping, jetting, nebulization, and so on. And since surface acoustic wave devices are based on thin film technology, they are also compatible with metamaterial realization. The photo on the left shows our first demonstration where a surface acoustic wave device was also used as a metamaterial-based sensor. So for doing so, we have placed the structure between two monopole antennas, and we observe the magnetic frequencies. And in the next step, we prepared different concentrations of glucose. And we could observe that by increasing the concentration of the glucose, the permittivity decreases, and therefore the effective capacitance will decrease, and therefore the resonant frequency will shift towards higher frequency. The same structure was also used as a physical sensor where it could also detect the location of a droplet. So for that, a droplet was placed in front of the IDTs, and when the droplet was further moved away from the structure, we could observe that the magnetic resonant frequency shifted towards higher frequencies. In order to use this structure for microfluidics, power was applied to IDT pads. And when it reaches a certain point, first it can generate streaming inside a droplet. To be able to observe that, we diluted polystyrene particles inside a droplet and then place a droplet in front of the IDTs. And we could observe the streaming inside the droplet. When we further increase the power, we could achieve pumping in DI water. And further increasing the power would also lead to an increase in the pumping velocity. In the next stage, when the power is increased high enough, it can lead to jetting of a droplet, which is shown in the picture on the bottom in the middle. In order to move our platform onto a flexible substrate, we first picked a piezoelectric polymer, which in our case was a PVDF. We characterized our device electromagnetically and also acoustofluidically. However, we realized that microfluidic functions are not achievable using this structure. And this can be attributed to two reasons, either because of its fabrication method. So in this structure, we used laser milling to create the structure. And laser milling can increase the local temperature, and this can deteriorate the piezoelectric property of the structure of the substrate, and therefore it won't be efficient for microfluidic functions. The other reason could be that it's still piezoelectric. However, since it's a polymer, the acoustic waves will substantially leak inside the substrate, and then they won't be effective to achieve pumping or other microfluidic functions. That's why we use a very similar structure, but in this case, we fabricated our devices on Kapton. So Kapton is a commercially available form of polyamide. And for our fabrication technique, we use standard lithography and lift-off processes. We characterize our devices electromagnetically. So on the left-hand side, you can see the simulation and the experimental results, and how a circulating current path is induced through simulations. To characterize our device for sensing functions, we prepare different concentrations of salt or NaCl, and then we could observe that by increasing the concentration, the magnetic frequency shifted towards lower frequencies. And this is because the effective permittivity and also the conductance of the medium is changing. In order to observe the acoustofluidic functions, we need a piezoelectric substrate. Therefore, we pressed our fabricated structure from the electrode side on a piezoelectric substrate, which in our experiments was a lithium niobate. And in that case, we could observe an acoustic frequency around 10 megahertz, which match our design specifications, because the acoustic frequency will depend on the speed of the acoustic waves inside the substrate and also the wavelength of the IDTs. So the speed of the wave is around 4,000, and the wavelength of our structure was around 300 micrometers. And by applying power, we could observe that we can see streaming inside polystyrene particles. So in conclusion, we propose the idea of combining metamaterial-based resonators with saw-based actuators using a single structure on a flexible Kapton film. We have characterized our device electromagnetically and have used it as an SRR to perform sensing experiments. We also characterize our device acoustofluidically by pressing this structure on a lithium niobate substrate and could achieve streaming at its acoustic frequency. The acoustic resonant frequency can be used for liquid manipulation, whereas the electromagnetic resonance is used for sensing functionalities. So the whole concept is advantages because it can be used for lab-on-chip applications. The fabrication is scalable and low cost, and it is suitable for flexible substrates. Our future work would be to optimize our substrate and also perform functionalization on the surface for specific detections. So this is my presentation, and I hope you enjoyed it, and I would like to thank you for watching this video, and I hope to see you in the conference. Thanks. Bye.